right, so we're continuing problem 3. All right, so this is really the change in the luminosity going from stage 6. Let me get my mouse here. Going from stage 6 to stage 4. Remember, the luminosity is decreasing by a factor of 7,901. Right, so it's going from from extremely bright to much dimmer. All right, so the equation that we're going to use is the change in luminosity is equal to 10 to the power of negative the change in magnitude divided by 2.5. All right, so we had a similar equation in past homeworks. So that, remember, this is going to be our change is 1 over 7,901, and so that's going to equal 10 to the minus the change in the absolute magnitude. Capital M is the absolute magnitude divided by 2.5. All right, so you just take the logarithm of both sides of this equation. All right, so that's this equation that we're talking about. And so you take the logarithm of both sides, bring the 2.5 over, and so it's going to be 2.5 times the log of 1 over 7,901. And so you get, and of course remember that you still get the negative, but really we're just interested in what the change in the magnitude is, right? So delta M, so the change in the absolute magnitude of a protostar going from stage 4 to a stage 6. Remember, at stage 6 it's just becoming a main sequence star, or about to become a main sequence star, is equal to a change of 9. So just do this in your calculator. Take the logarithm of 1 over 7,901 and then multiply that by 2.5. You're going to get a negative 9.74. But remember, you got the negative over here, then that'll cancel. It's in other words, it's going to increase the absolute magnitude by 9.74. Right, and remember, an increase in absolute magnitude means it's going to be a much dimmer object, right? So that's the change. So that's the change in absolute magnitude. All right, let's continue on with number 4. All right, here's number 4. So let's see, it says, what is the approximate absolute magnitude of a stage 5 protostar? So what we're going to do is we're going to look at, and we got to look at figure 19.6. All right, so there's some interpretation that is left in this particular problem. So I don't think it's not the best problem, if you ask me, but anyhow, let's go ahead and do this. So when I look at this figure, so you got to estimate what the luminosity of a stage 5. Okay, so this is of course stage. That's supposed to be an A. Stage 5. All right. So I'm going to say the luminosity, and again, this is open. It depends. It's not the best graph. Let's say it's 25 times the luminosity of the sun. All right. So that's the sun luminosity. So that's what we're going to plug in. All right. So and we're basing this since we're basing this off the sun, we've got to use the absolute magnitude of the sun. All right. So this is basically this becomes 25. Of course, you're going to take the logarithm of that. You can take the logarithm of both sides, and so this is the logarithm of 25. And then we got to bring this 2.5 over. This 2.5 has to go over to the other side, so this becomes 2.5 times that. And so what does that all equal? All right, so that's going to equal, let's see, it's going to equal negative M, right? So that's the absolute magnitude of this stage 5 protostar, plus the absolute magnitude of the sun, which is 4.83. All right, so you have to, you bring this over to the other side, And here, what do I get when I did this? So let's see. So when I did it, I get capital M turns out to be 1.34. 1.34. All right. So yeah, that's the basic thing. Yeah. All right. So oh, let's see, I think we want this to be positive, actually. This is positive right here. And so that makes this negative, so sorry about that. And then when you bring it over to the other side, you add that. All right, so, all right. Yeah, so that's number 4. Again, not my favorite problem, certainly. Okay, so here's number 5. By how many magnitudes does a 3 solar mass star decrease in brightness as it evolves from stage 4 to stage 6? And so again, we have to look at this figure, which is 19.7. So when I did this, again, this is open to interpretation, just like the last problem. I'm saying that it goes from about 1,000 times the luminosity of the sun to about 400, or to 40 times the luminosity of the sun. Right? Again, it's not perfect because you got to interpret the scale, but this 40 divided by 1,000, of course, turns out to be 0.04. Right? So 0.04. All right, and so that is going to equal. Remember what we're trying to figure out: how many magnitudes. So this is like the change, the change in L, and so that's going to equal, 10 to the, let's see, what is it? 10 to the negative. The change in the absolute magnitude. Plus 4.83 really, and then of course divided by 2.5. Right, we've used this several times now. All right, so you take the logarithm of both sides, so it's going to be 2.5 times, right? The 2.5 of course comes from over here. 2.5 times the log of 0.04. All right, so that's basically the idea here, and so that's going to equal, well, let's see, that's going to equal negative the magnitude, and then you're going to bring a negative 4.83 to the other side. So this is going to, this is going to be negative anyway, and then plus a negative 4.83. So here's approximately what I get for the magnitude. By how many magnitudes does it change? It changes by negative 8.3. Negative 8.3. All right, so that's number 5. Let's do the number 6. All right, so number 6, using the HR diagram in the chapter, estimate by what factor a 1,000 solar luminosity 3,000 Kelvin protostar is larger than a main sequence star of the same luminosity. Okay. All right. Larger than the main sequence star of the same. I think they don't mean the same luminosity. They mean the same temperature. Okay. So anyhow, if they're both the same temperature, and you look up so basically it's really, really simple. So this is going to be the square root of 1,000, right? Basically 1,000 divided by 1, and so that is approximately, when you take the square root of 1,000, it's approximately 30. All All right, so the radius of the protostar is approximately 30 times the radius of a main sequence star of the same temperature. All right. Let's move on to 7. All right, so here's number 7. What is the luminosity in solar units of a brown dwarf whose radius is 0.1 times the radius of the sun and the surface temperature is 600? All right, so we're using this equation right here. We're just assuming that, so they give us all the numbers. So it's really 0.1 squared times the temperature of the star, which is really a brown dwarf, divided by the temperature of the sun. And so that's going to be, whatever that number is, it's going to be multiplied by the luminosity of the sun. So to solve for this, so remember, this is the luminosity of the brown dwarf, right? So for the brown dwarf, when I did this, you're going to see, of course, this is incredibly dim compared to the sun. I get 1.15, that's supposed to be a 5, times 10 to the minus 6th times the luminosity of our sun. All right, this is indeed a very, very dim object. Let's do number 8. All right, so here's problem number 8. Let me read it. It says, what is the maximum distance at which the brown dwarf in the previous problem, problem 7, remember the brown dwarf is 0.1 solar radiuses. That's really important for us. So in other words, this r here in this equation should be 0.1. Anyhow, let me continue to read it. The previous problem, observed by a telescope of limiting apparent magnitude of 18 and 20. Okay, so we had this formula before. You might remember this was another earlier chapter. All right, so you just put in remember, because it's the inverse square law. You put in the size of the object compared to the sun, and then you were using these numbers. Of course, there's the absolute magnitude of the sun. This is the apparent magnitude of the star, of the brown dwarf, the limit of what the telescope can do. So in part A, it's 18, and then part B, it's a little bit dimmer, all the way down to a 20. All right, so let's just put the numbers in and figure this out. All right, so for part A, when the telescope has a limiting magnitude of 18, positive 18, of course, then what we do is we take the radius of the star, which turns out to be 0.1 times the radius of the sun. We're going to square that. We're going to take and then 10 to the and so the apparent magnitude that is limiting our telescope is going to be 18, and then we minus the 4.83. Remember, that's the absolute magnitude of our sun, and then divide by 5. All right, so when we do that, here's what we get. Let's see, what did I get? I get, I gotta get my calculator. All right, so I got my calculator. So you 10 to the 18 minus 4.83 divided by 5, and then that turns out to be, remember the answer, by the way, comes out in parsecs, all right? It turns out to be 430, and some change. And so you multiply that 430 times 0.1 squared, you get that this brown dwarf could be 4.3 parsecs away. All right, for a telescope that has a limiting, you can only see stuff down to about a positive 18th magnitude. All right, let's do the last one. All right, so I've set up the second equation for a magnitude, the limiting factor as a magnitude of 20. So again, it's the same equation, 0.1, because that's the size of the star, squared, 10 to the 20th minus the absolute magnitude of the sun divided by 5. So that turns out to be 10.8. And remember, this is in parsecs, so 10.8 parsecs. So with a telescope that can see to a magnitude of 20, you'd be able to pick out a brown dwarf